Inertia is a fancy word for an object's resistance to change in motion. Think about it. A heavy bowling ball is harder to move than a light tennis ball, right? That's inertia in action. Moment of inertia is similar, but instead of just moving in a straight line, we're talking about an object's resistance to rotating. Imagine spinning both the bowling ball and the tennis ball. Which one would be harder to get spinning quickly? You got it, the bowling ball. This is because it has a higher moment of inertia. The farther the mass is distributed from the axis of rotation, the harder it is to spin. Moment of inertia is important in tons of real-world applications. Think about figure skaters spinning. When their arms are pulled in, they spin faster. They've reduced their moment of inertia. Now, let's talk about centroids. Every object has a balancing point, a point where it would balance perfectly if you could magically support it from that single point. That balancing point is the centroid. For simple shapes like a square or a circle, the centroid is right in the middle. But for more complex shapes, the centroid might not be so obvious. Think about a boomerang. It's got that funky curved shape. Finding the exact center of mass, the centroid is a bit trickier. So how are moment of inertia and centroids connected? Well, an object's moment of inertia depends on both its mass and how that mass is distributed around the axis of rotation. And guess what? The centroid plays a key role in understanding that mass distribution. For shapes with uniform density, the centroid is like the average location of all the tiny bits of mass making up the object. The farther those bits of mass are from the axis of rotation, the higher the moment of inertia. Imagine a rod rotating about an axis through its center. Now imagine that same rod rotating about an axis at one end. The mass is the same, but the moment of inertia is higher when the axis is at the end. That's because, on average, the mass is farther from the axis of rotation. Moment of inertia and centroids pop up everywhere in engineering and design. Think about designing a sturdy building. Engineers need to consider the centroid of the building's mass to make sure it's stable and won't topple over. Or, think about a bicycle wheel. The distribution of mass in the wheel, particularly in the rim, affects its moment of inertia. A wheel with more mass concentrated in the rim will be harder to accelerate, but it will also maintain its momentum better. Understanding these concepts helps us design better, more efficient and safer structures and machines. And that's pretty cool, don't you think?